Hello. This is an odd setup, but I'm going to make it work. Today's lecture is about high-performance computing systems and running simulation studies on them. And I'm going to share an anecdote to begin with prior to this. When I was a graduate student back in the dark ages of 2004, I was working on my dissertation, and I had a simulation study as part of it. Actually, I had a couple simulation studies as part of it. And at the time, I had a computer, and I knew that I needed to run lots of simulation. And sure enough, the simulation was going to clog my computer so that I couldn't get anything done. So I then used my credit card, of all things, and went to the Dell outlet online and bought 3, as cheap as I could find, Dell computers and put them in my home office. So my desk had actually 4 different boxes turned backwards on a desk of computers. I had a monitor on the top with a cable that was dangling. I had a keyboard and a mouse with cables that were dangling. And I would plug each of those 3 implements into the back of the computers. And then I would go and work on each to get a series of simulation files running on each. And if that sounds clunky, it was. It took a long time, took a lot of effort. I paid a lot of money for those computers, even the outlet price. And not only that, it was really inefficient. I also had to pay for the heating and the cooling of my house, because as you imagine, 4 computers in your room, it's going to get kind of hot. So if only I would have known. I worked at a place that had a supercomputer. It was, in fact, if you go to most web browsers and you look through sort of the details of each, they list the National Center for Supercomputing Applications at the University of Illinois. That's where I went to school. Had I known about the supercomputer, not only would I not had to pay as much money to buy these little computers, I would have been able to get things done much faster. And that's why I believe in this and why I want to teach you about this. Supercomputing or high-performance computing systems help in 2 ways. They help you run lots of different small analyses simultaneously, and they help you run big analyses. And the irony is, when I was a student at Illinois, I had a data set. I was doing a data analysis, a social network analysis, where I had like 250 million data points. I mean, it was massive. And I was doing versions of a logistic regression on it in MATLAB. And I had acquired an account on this supercomputer to run this because I couldn't run it on any desktop. So that's the beginning story. The other story that I tell you this is class, right? So basically it becomes my story time, right? Stop me if you've heard this before or you've seen this before, but I've since had a few jobs since I left grad school. And in every job, since I'm a quantitative methods researcher, there's a lot of simulation going on in each of those jobs. And sure enough, with the jobs, I have seen students who will also be in the same situation. And so they will find computers anywhere they can, and they will put little signs in front, "Do not use simulation running." Have you seen that before? Or they will borrow their friends' or they'll do everything they can to run computers, or they'll run it on their own machines. So it's using someone else's computing system is great because effectively the way that we interact with it, there's data files, which are large, but just to make it work and to make things run are a series of text files, which means you literally can be doing this on a mobile device to access the high-performance computing system, and you could have all of your dissertation or master's or research simulations run on it without having to literally open an actual desktop anymore. So it's cool in many ways. Plus, the university pays for it, and you get free accounts, and you have access to it. So let me go through that. So today we're going to talk a little bit about the overview of high-performance computing itself. This is specific to the University of Iowa's Argon cluster, Argon High Performance Computing, or HPC system. There are other Mechanisms for high-performance computing, generally speaking, they work very similarly. And if you're on a research campus like ours, a university like ours, there will be subtle differences on how you set things up, but most of them work the same. If you're in industry, you may encounter similar types of systems. However, the way that you schedule jobs and make things run will be slightly different. And I don't have the specifics on that right now because I don't want to pay for Amazon Web Services to show you how to do that. But it does work very similarly for the most part, sort of structuring how your programs work. So today we're going to talk about what is a compute cluster, high-performance computing itself, high-throughput computing, and differentiate between these two sort of use cases of compute clusters. We're going to talk about the Argon cluster here at the University of Iowa. And we're going to talk about mapping your problem to a cluster. And I will note that I am taking these slides from a presentation workshop that we presented at in the College of Education just a little bit over 2 years ago when I was brand new here at the university with a colleague named Ben Rogers, who is part of the university's computing group. And he's moved up the ladder, and I couldn't find him now. But I'm assuming that he's okay with me adapting his slides or the HPC workshop slides for our uses. So I will also note that if you are on the University of Iowa's campus, they often hold workshops like this frequently. So the HPC group, Research Computing Group, will hold these workshops. However, I'm discussing it here in our course because it will be more tailored to the jobs that we're used to running, I think. So I think that's important for us. I also think that each of you who has either a very large data analysis or has a simulation study or wants access to software they may not already have, this is for you. So this is where we're going. Okay? Questions? All right, moving forward. If you are interested in instructions and resources, you can find this wiki documentation link there. And for cluster help, research-computing@uiowa.edu is the place to send a message to. And I will note for those of you in my course, we have a course account to access Argon. If you haven't signed up for your own individual account, however, once this course is over, you will lose access and you'll have to go to the Wikipedia or that wiki right there link to figure out how to sign up for an account itself. I encourage you to do so if you think that you will be using any of this after class is over. So if you haven't done so already. Okay, what is a compute cluster? A compute cluster is simply a very large number of computers, in addition to software that allows them to work together. So, believe it or not, in the basement of the South Lindquist Center, there is a very loud room. In fact, when you walk in on the first floor, you may hear fans whirling about. And those are the fans that are cooling a large set of cluster racks. Those are a series of racks where they have blade clusters, like computers that are put inside. And when I was interviewing here, I have to go and look at high-performance computing everywhere I interview because I use it so frequently. So they arranged for me meeting actually Ben Rogers, the guy who made these slides. He took me into the basement, took me into this place, and it was awesome. They have this section of the room that's super cooled. Like you go in there and it's like 60 degrees because everything is creating a lot of heat. And so they're cooling the machines with that. And then, of course, they have to take the heat and put it somewhere else. They have another section of the room that's like 120 degrees. It's incredible. It's like you go from like summer to spring or fall, all in the section of the room itself. And it's all, well, many of you just had to relocate because you were on the first floor of South Lindquist, and now you're in Bell and Blanc. But it's all right beneath us. Effectively, it used to be right beneath us in the Lindquist Center, and not all of it. Some of it's there, and some of it's housed in a different location. That's the other nice thing about this, is that this compute cluster is housed somewhere, and we access it via the internet. So we don't have to be physically present for it. You don't have to be like me in grad school and plug in your keyboard or your mouse or your video. By the way, there's such a thing called a KVM switch, keyboard video mouse switch. I didn't know about it in grad school. I since came to know about it, but then I learned about compute clusters, so don't need it anymore. So compute clusters are tools for solving computational problems that require more memory or CPU than is available on a single system. Some of you will have run, this is sort of what we call the high performance version of the use case. Some of you may have data analyses that are just so large that you run out of memory. Have any of you exceeded memory on your system before? Particularly if you're using the program called SAS, you may get an out of memory error, which is frustrating. This is a way you can solve that. Okay, moving forward. So high performance computing is using multiple computers in a coordinated way to solve a single problem. All right. So inside the computer, let's talk a little bit about what's inside. There is the computer chip itself, right? And the chip itself is the part that does the processing, that does the work to do computation. But each computer chip is subdivided into a series of what are called cores. All right, a core is like the smallest unit of that chip that works. So I have here. If you take a look at my Mac Mini running here, I actually have I believe a 6-core or an 8-core machine. Actually, no, I believe it's a 12-core machine here. This is trying to tell you what I'm doing for what I have, but oh, anyway, can't show it to you. Long story short, the core is sort of the smallest unit of a CPU, a compute chip. That core will do a lot of computations itself in serial, like one after the other. And if you have, most chips these days have multiple cores on the chip itself, so that's how you'll run things in parallel, so parallel processing itself. And so in this high-performance computing system, going back to that picture from before, this is a room where a bunch of each one of these towers right here is a series of these blade servers. They're just long computers. In there is a chip, a CPU chip, and that chip may have 56 cores in it, right? So 56 compute versions to it. And why that's important is if you're running a bunch of simulations, if you just did things without splitting it up, you would have, if you ran, let's say, 56 analyses, you could run 56 in a row on one core, or you can turn all 56 cores to run one at the same time. And you can imagine that latter process will speed things up immeasurably, all right? Well, actually, measurably, it will make things considerably faster, right? So the goal in high-performance computing is to parallelize or create processes that run at the same time, and do so not only on the cores of one of those machines that are in a rack, but potentially across racks as well. All right, so high performance computing is the term that gets used when you have a really large data analysis. You have a ton of observations, or you have a really complicated model, or both. And it allows you to use, so the Argon system allows you to use tens to thousands of cores to solve a single problem itself. Not only that, this Mac Mini that I'm running this lecture from came with 8 gigabits of RAM. I went and installed 64 gigabits of RAM. So another part of the computer system inside is RAM. It's memory. It holds the numbers that are about to be processed. And it does so electronically, so if the power goes off, everything that's held in it goes away. That's opposed to a hard drive or a solid state drive that hold things without power. That it gets written to it and then gets drawn back from it. Having things in this physical memory with power means the data move faster to go get computed and back and forth. And so each of your drives, each of your laptops, each of your home computers has a set of RAM. I've got 64 gigabits here. That seems to be, for most of my uses, fine. However, there are cases where I may need a whole lot more, and you can throw on there, quickly put together a job or an analysis that would have 1,000 gigabytes of RAM. So that's nice, right? For those of you who are who buy your own computers and think about this, what do you think of 1,000 gigabytes of RAM? Pretty nice, huh? I see people shaking their heads. Yeah. Anyway, so yeah, I'd like 1,000 core, 1,000 gigabyte machine, please. Nobody says that, right? But that's how it works with the supercomputing system. So that's the cool side of it. The drawback of it is, in a lot of cases, you have to have software that allows you to take advantage of multiple cores and multiple sources of RAM. There's sort of two large, at least two large software frameworks that do this. One is called MPI, Message Passing Interface, and the other is OpenMP. That is less of an issue for what we do in our class because often we use other people's code to do this. So for instance, I do a lot of Bayesian computation, and when I write Bayesian code in R, I use the parallel package to create these worker nodes to run analyses in parallel. So R has taken the load off of that for me. If you're in SAS, if you're trying to run like a mixed model in SAS and you run out of memory, believe it or not, there's actually a proc HP mixed in SAS that allows you to take advantage of high performance computing with mixed, and there's other features of it as well. The other thing I wanted to note before I get too much further is there's another system of cores that gets used, particularly in machine learning applications, and that is a graphics card. And so it turns out our high-performance computing system has a bunch of graphics processing units, GPU. So CPU is the computational processing unit. GPU is graphical processing unit. But it turns out a graphical processing unit is a bunch of is a card. It's like a chip with a bunch of cores, even more than your CPU would have. And so even though most access to Argon will not have any graphics whatsoever, you can request graphical processing units to do your analyses because particularly for machine learning or neural network type applications, there's a lot of ways that you can quickly run the analysis by spreading out computation to each of those cores on the GPU. And there are other frameworks that allow you to do that, one of which is called TensorFlow, which allows you to go and quickly access cores of a GPU as well. So, questions so far?
So are you using the GPU to do the CPU's work, or are you using it for graphics related stuff?
In high performance computing, the GPU is used to do the CPU's work. And so that's actually a great question. When you're if you're on your local machine, your GPU, for those of you, I'm guessing the times I hear of GPU is when people are like into gaming, like my daughter, who's 14 at the moment, and this pandemic has really, really enforced her love of being online with her new friends online, right? And she needs to have GPUs set up so that she has a certain frames per second, right? All that is computationally expensive to draw things on your screen. Well, it turns out the same the GPU itself doesn't care whether it's drawing things on a screen or optimizing an artificial neural network. It works the same. The only question is how do you access it? So in the high performance computing system, we're literally using those graphics cards to do CPU work, and that's because a graphics card itself can fit more cores on it than a typical CPU will have. So you may have they run a little bit slower, and sometimes each core itself may run substantially slower. But because there's so many of them on the card itself, that people find that valuable, particularly for neural network problems where each layer of nodes may be a separate computation.
Okay, that's interesting.
Any other questions or thoughts about this? Okay. In these slides, the examples that he gave were computational fluid dynamics and molecular dynamics. And I'd like to add psychometrics. That's right. Psychometrics is what we can use this for. Thank you very much. Okay. So moving forward, the alternative to that, so the differentiation that gets used is high-performance computing, which is I got a big data analysis to run. Lots of data, need lots of memory, need lots of cores to just provide one analysis, right? The alternative is I've got a little tiny data analysis that I have to run thousands of times. And that would be called high throughput computing, right? So in the previous weeks of this course, we've talked about design of simulation studies. In this one, we're talking about high throughput computing specifically for those simulation studies themselves. They fit that mirror, right? Where each replication of a simulation study would be a separate process on the supercomputing system. All right. In the examples I showed you before, I did, for the very first part where we had discrete factors, a factorial design with discrete factors, we had some 15,000 replications run in total. What our setup for the supercomputer would be, how can we run as many of those at the same time as possible? It didn't take long. I mean, these were regression analyses just to get us off the ground. So it didn't really take a long time to get moving. However, those were very, other types of psychometrics will take much longer. In fact, most of the things I do take a lot longer. So having the access of the supercomputer to run, let's say, 80, 90 of them simultaneously would be a big benefit. So the slides mention having the ability to analyze many data sets simultaneously, efficiently perform a parameter sweep, if you know what that means, requiring minimal code modifications. So this is the nice part about high throughput computing is that you don't need to modify a lot of what you've done. You just need to run it multiple times and set up the input to the the HPC system a little bit differently. And here people talk about using image analysis or genomics, and I'd say simulation studies for us too, although I didn't modify this slide. So, questions? Okay. So here is the Argon cluster. This is a collaborative cluster. It runs on a Linux operating system named CentOS 7. So tying this in our class back to the quick intro to Linux that I gave you before, this comes in handy. That's why we did it. As of 2019, these are the specs that you see here. Lots of cores, lots of threads, all that stuff. There is storage. You get when you sign up for an account for free, you get about a terabyte of storage. If you know what that is, for a lot of what we do in psychometrics, that's sufficient. But if you need more, you can end up paying for more. I end up going for more on my own version of it. Maybe. Sorry, the delay in slides. And of course, there it goes. Keep going. There it is. Now, talked about Argon. We've talked about the storage. The big hurdle for accessing Argon for a lot of what you have to do is to get your data onto Argon itself, or in our case, even if you're doing simulation studies, to get the text files that run the simulation onto Argon. And so there are a number of different steps to do that. I can't show you the Windows steps because my little Mac Mini is already working as hard as it can. However, if you know about how to connect or to map network drives, you can do so following this instruction right here. If you're familiar with Secure File Transfer, or SCP, you can find the link there. If you are, but the main thing is you need to be part of the VPN first. So let me just connect to the VPN for just a moment. And again, everything is delayed as I'm recording in multiple features. I'm going to practice patience. Not my strongest attribute, let's put it that way. And now I'm on the VPN. For those of you using Mac, this is a demonstration that is geared toward the Mac because I use it. And honestly, I started using Mac more when I started to have to connect to these HPCs. If you're using Mac, you can access Argon by going to Finder. So if you just click on like your desktop, once you're part of the VPN, if you go to connect to server, it'll pop up a box. Here you can put in the link that I had shared right here, which is data.hpc.uiowa.edu, argon_home. Don't have it there. So what ends up happening here is data.hpc.uiowa.edu. You hit connect, it thinks about it. May think for a little bit. And then it'll ask your credentials. You put in your Hawk ID and your password. And sure enough, in just a moment, what you will get is a drive that shows up, at least if you have the setting for it, on the desktop. It'll open a window, and in that window, that is my files. Those are my files that are on the server itself. So if I just want to drag things over and put them in there, it looks like it's part of my own local file system. For those of you on Windows, this mounting of the drive itself is also similar to that. So it'll work with Windows Explorer. So if you're familiar with that. Now, for class though, because in our previous history with dealing with in particular Git or not, what we're going to use is this secure SFTP, or Secure File Transfer Protocol. And to do that, I recommend using this client called FileZilla. FileZilla is an open source and free file transfer application. And what FileZilla looks like, actually let me go back, follow along with my slides here to make sure that we're all on the same page. Maybe, there it goes. We are going to go to FileZilla first. You download that application from FileZilla itself, and I'm going to bring that up. It looks like, patience. There it is. Okay, there's FileZilla. This is my local downloads file. If I want to connect to a server, again, I have to be on the VPN. Actually, I don't have to be on the VPN for this, but what I'm going to do is I'm going to click a new site button. So you click up this button at the top left. You go to new site. We can call it Argon. And in the settings for it, we go to SFTP. Our host is, and this is where I need to look for it, argon.hpc.uiowa.edu. And here's the key thing. It's port 40 that you use. Port 40 actually allows you to not be on the VPN and allow you to connect without having VPN access, which is awesome. And here we'll put our username as your Hawk ID. If we hit connect, it'll ask you your password. And then it will actually it'll ask you to trust the host, which is, I will say yes, because I know where I'm connecting. It will then send you a Duo link. You can see it on my watch here, that you have to approve with two-factor authentication, and boom, there's my Argon folder right there as well. And so similar to what I just showed you before, now if on the left-hand side of this window is my local machine files. On the right-hand side is Argon, and if I wanted to move a file over to Argon, I just click and drag it over. Or actually, no, double-click it. You'll see that it transfers. You'll see this bottom part right here where it transfers. Actually, it asks for two-factor authentication for each one of these. That's inefficient. Okay, questions on this so far?
I have one thing to
Yes.
remind. If you log in from off the campus, I think you need to have two passcode. But the first one is just your username and your passcode for yourself. But second one is from the school, which will be push, Push, small letters, push.
That's right. That's
Okay,
right.
thank you. Because yours, I noticed you don't have that access. So I mean that
I
reason.
used the PUSH for the when I connected to the Cisco server. Yes.
Okay, thank you.
Thank you, Mingying. Anybody else have questions?
Yeah, so the first way you showed didn't require VPN either, did it?
It did. The first way
Okay.
to connect so that you can see, this is like in Windows, I think Farhan, you use Windows. This is mapping a drive, a network drive. So you'd need to be on the campus net, the VPN, to make that work. And Mac, you'd also have to be on the, actually, regardless of the system you're on, you need to be on the VPN to see it with your own network, your own computing system itself.
Oh, okay.
All right. Other questions? Well, here's the fun part. So that part I went over a little bit quickly because we don't need that for today. Today we're going to go way back into the Wayback Machine and use the command line. What? Yes, the command line. So what I'd like you to do to follow along is to go to the notebooks site, notebooks.hpc.uiowa.edu. And here we're going to go into our course notebook, Topics in Educational Measurement Statistics. It'll ask you to log in, which you will do. And it will, of course, need to authenticate with two-factor authentication once it logs in. And there it goes. Doink. And, oh, I need to start my server. I know that some of you had issues with this working last week. I hope they have fixed them. Otherwise, today is going to be sort of destroyed. So, there's our studio. Do you have our studio? Do you see it on your end? Great. Okay. We're going to work with the terminal window again today. So to find terminal, you have to look by your console. If it's not there, you can go under View and move focus to terminal. So once again, View, move focus to terminal. That will bring up your terminal window itself. And just to follow along with the slides, the slide right after this is... There. Oh, come on, you can do it. Move forward. There it goes. Nope. Move forward 2 times. Not do that. There we go. We're going to use this SCP method to move files over. And our goal is this. I have an example demonstration file right here in class data, HPC. There's this argon demo.tar.gz. Tar.gz, if you're not familiar, is a compressed type of file. It's called a tarball or gzip tarball. That we often use in Mac or Unix or Linux systems. I'm sure you've seen them before even on Windows, but just in case, that's where they come from. It's the Unix equivalent of zip. So we go to the terminal window, and it turns out, if you remember a little bit of your commands, if we type ls, it shows where we're at, the folders that we're at. And pwd shows us our current location in the file system. We just need to take the text that's listed right here and put it into the console. So let's do that. scp-p 40. So scp is a file transfer mechanism that you can use through the command line. If you're on Windows using the Windows terminal, I don't think it's installed, but on Mac, through the terminal, you can do this as well. The -P option tells you to use port 40, which actually avoids the use of VPN, which is much more convenient. And then we type in the location of the file on our current machine, so that would be tilde slash class data HPC and then argondemo.gz. And if you're wondering how it's if you remember the commands, if you just start typing a few of the letters that need to be there and hit tab, it should fill out the rest. The next part of this is to give it your Hawk ID and then @ and now instead of like an email address, it's actually going to be argon.hpc.uiowa.edu. So what this is trying to do is log you in to this Argon system. So mine would be jtemplin at argon.hpc.uiowa.edu. And now the last step of this is a colon. And we put the name of the file that we want to name on the system itself. Technically, this is the location of the file on the system, but we're going to just call this Argon demo, and this is where we have to type it all ourselves, .tar.gz. So do you see all that? Is this clear enough, or do I need bigger font? Just in case, make it a little bit bigger. Now, once I hit return on that, it'll ask my password. This is my university ID password. And again, it'll do the duo two-factor authentication if I've typed it in correctly, which I have to approve. That's odd. I have no such file or directory. What did I type in correctly? I love this. Okay, let's pretend it worked. What did I do wrong here? HPC Argon demo.tar.gz. Yeah. Interesting. Okay. Well, if this isn't working for you, I will get it fixed at the break and we'll make it work again. You can see I use SCP so frequently that I don't know it. But now, if it were to work correctly, we should have moved this file over into Argon. And in fact, when I did try this out and it did work, well, I guess it didn't work. Never mind. It's not there. Okay, well, I'll get it set up. It's just a problem with my SCP command. We'll go from there. Questions on this ahead of time? This, by the way, is why I organized our class schedule to cut out more things. No file. Okay. Thanks, Jing, for telling me that. Okay. So let's go a little bit. Yeah.
I'm getting that I don't have a directory of, hang on, let me find it. argondemo.tar.gz, not a directory.
Okay, let me get back to you on that after break, and I will have more information about it. I will be furiously trying to record this. What's that, Jihong?
I have access.
Oh, you just put a tilde there. Is that right, Jihong? Okay, let's try it. Thank you, Jihong. You're always the savior of these examples.
It also works for me as well. I think
and there we go. No such file or directory. Nope, there it goes. Okay, so here's the thing. On your SCP line, if you're in your terminal, your R notebook or your RStudio notebook, if you press up, what Jihong has suggested, and correctly so, is that you remove the argondemo.tar.gz and replace it with a tilde. What that tilde will do is it provides you your root directory on the remote computer. And if this had worked correctly, if I go to my Argon home window, and there it goes, it updates. You'll see now on my Argon, this is my Argon file system right here. There is an Argon demo file that is moved up there. So you won't be able to see it on yours. It'll just say it was. You will see. Hopefully, what you will see is this 100% line right here. This is the upload itself of the file. So we can't rename the file, but we can at least upload it. Does everybody get that working? Thank you, Jihong. Xing got it work. Farhan got it. Hooray. Now, we'll get there. What's it?
Yeah, mine works before you.
Even better. Thank you, Mingying. So, that means you have to trust it's there. We haven't gotten there yet to go find it, but we will. And this will come in handy next week, because next week is when we actually unpack that file to run our simulation on the server. Uh-oh. Try again, Shinji. Sometimes it takes a while to push a duo request. I'm going to pause for a moment. Anybody else have questions or comments on this? If you got a lost connection, not sure what the issue is. Hang on that note. It could be that you somehow did not get authorized to have access. I know I've corresponded with a couple of you about that, but it should be able to work. But don't worry, we will get there. We don't need this file this week, actually. So the good news is we will use it next week. Okay, so I'm going to go back to the slides now. And if you still have problems with that file, we'll work on it either through break at the end of class or at the beginning of next week as well. So the question is, it just runs faster, right? And the answer is no. In fact, many of the machines on Argon are actually slower than most of the machines that you might be using that you'd buy today. In fact, the way that they do things is I believe the server life is about 7 years on Argon before they replace them. So you may have a chip that's older. Just running at an Argon for a single analysis will not necessarily make it run faster. But here is the thought. Let me show you an example actually coming up here. Here are the questions you need to ask yourself when you are thinking about mapping the analysis to a cluster. Does your problem require more resources than available on your desktop? Right, this is for the high performance example. And for a simulation, I'd almost argue all the time it does. Unless you just can run it like in 3 seconds like we did with the linear regression in class. Next question, does your job run on Linux? Turns out most of what we do will run on Linux. There's a Stata version on Linux. There's SAS on Linux. There's R on Linux. There's MATLAB. You have access to all of those if you have access to the cluster. So pretty much most of those will do. Plus, of course, the cluster. If you're building your own, you like to roll your own program in Fortran or C++, Java. I think all of those are on the cluster as well. In fact, when we get to the cluster, you'll see there's a ton of software on it that you can use. So pretty much anything can run in Linux itself. Can your job run in batch mode? Most of what we do for software and psychometrics is yes. That means can we run it from the command line? And most of what we do can be done. Is it a high performance job or a high throughput job? Most of what we do will fall into that as well. There's some quick analyses. If you're running an IRT analysis on a single data set, probably not going to be hard to run on your local machine. Probably wouldn't want to spend the time it takes to run the HPC. But for a lot of what we do, HPC works great. So the next steps are to develop a strategy for running jobs, to install software if you need to develop your job submission scripts, and then to run your job. And I'm going to show those to you in our example when we get up online next. I actually have an IRT example I developed to show us how to run IRT jobs. Moving forward. Nope, that's not what I need. Click there. Okay, so here's an example of running things faster. If you were trying to analyze 1,000 MRI images, there's a program called FreeSurfer. It takes about 20. So an MRI is just really data intense. It's like terabytes of data that go into it, right? So it may take 20 hours per MRI and 2 gigabytes of memory per analysis. So if you did all that, if you're trying to look at these images, not that we have anybody who's doing MRI, but you never know. Could happen. 20 20 hours, 1,000 MRIs would be 20,000 hours, or 2.3 years consecutively on one machine. That doesn't sound good. And you may be thinking to yourself, wait a minute, I don't do anything with MRI. But instead of MRI, think of data analysis using MCMC, or think of the newest, craziest IRT model or model that just came out that takes a long time to run. That would be it. Oh, and as an aside on that, this morning I woke up and looked at email, and I got an email from a Advances in Veterinary Medicine journal wanting me to review a paper where people used IRT on cows in Sweden. I kid you not. So you never know when an MRI might be in your future. If I'm getting veterinary medicine articles, I had to decline the review. I will say that much. Anyway, so if you take this same problem and map it onto the Argon cluster, you can run each of those analyses. In theory, if you had 1,000 processor cores, if you had access to it, you could run all those analyses in as little as 20 hours. Now, you won't actually have access to 1,000 cores unless you pay for it. That I'll get to how Argon works for resources in just a moment. But it's conceivable that you took that really long 2.3 year problem and cut it down to 20 hours and get it done in a day. All right, that's not bad. And so this is why, particularly, I can't tell you the number of times I've been on dissertation or master's committees where the committee will say, yeah, but if you add this condition, you'll never finish, or blah, blah, blah. Actually, there are ways that you can get more complicated or better research done and get it finished. It's a bigger question as to whether you should scientifically do it than it is pragmatically of will it run fast enough, because Argon is a way that you can get it to run fast enough. Case in point, in the week between Christmas and New Year's, I wasn't planning on doing a whole lot of work, although I was working every day. And in that time, I decided to be a good time to run a simulation study. I had 72,000 analyses get run in that week, and each analysis took something like 3 to 4 hours. So it was pretty cool. It's like, oh, well, I just, sort of monitor it here and there. I can log in and check pretty quickly, and sure enough, got all that run. So Argon makes complicated or time-consuming research go much faster. So what happens in Argon is to make an analysis run, you have to create what's called a job. And then that job gets submitted, and it goes into this program called the Son of Grid engine, which is what's called a scheduler. The Son of Grid engine looks at all the machines in the server, and it schedules analyses to run depending on the resources needed for each and the permissions each person has, right? So basically, let's say I need 1,000 cores to run this job. It will go and figure out the next time 1,000 cores will be available, and it will schedule your job at that time to run. And then it will run it at that time or sooner, depending on how resources shift. So what that means is you may need to know a little bit about a queue, which is sort of the line. So the server itself, the server system itself, is paid for in part from a little bit of university funds, but investigators pay for servers, and they have a price list online. And if you pay for a server on Argon, you have priority access to that server, meaning you go in, you submit a job. If you tell it to run in the queue or the line of your server, it will run immediately if you have the resources. That means anybody else's job running on your server right now gets kicked off, gets deleted actually, ends abruptly. Evicted, I believe they call it. The job is evicted. So if you're using if you have a lot of things to run, so I have my own queue, and for the students I work with, if you have a high priority task that you can't quite get access to in the rest of Argon, I'm more than happy to share my resources with you. I know Dr. Aloy has some. I think the Iowa Reading Research Center, because of Dr. Aloy, has a queue pays for resources. But anyway, if you don't pay for the resource, though, you have access to anybody's unused resources. And it turns out, more often than not, that's way more than you need. It'll let you run 80 to 100 jobs at a time if it's high throughput. If you're doing simulations that take a couple hours each, you can get most of your simulations done. Yes, a lot of those will get evicted, but you can just rerun them at a different point in time. And so just knowing that ahead of time makes it work. You have to know how many slots. A slot is like a core. How many cores you need for your analysis. In this case, just knowing how to parallelize the software. For me, I mentioned before, I run Bayesian analyses. If I'm running a Markov chain, I like to run 4 chains. So I would request 4 slots or cores to run that, 1 in each core. And so it will run each of those at the same time, or it would run about 4 times faster than it would if I ran them just in sequence, in serial. Other resources you may need also include the memory, the RAM of the computer itself. And so if you have a very memory intensive, have a large data analysis or have something else, you may ask for much more memory than comes as a default. And I'll show each of this to you in just a moment. Any questions on that? Okay, so here's how they set up things. There's a bunch of queues. Again, those are lines, or those are resources that are owned by investors or investigators. There's a general queue called UI, which means you can run up to 5 jobs on UI, and they will not get evicted. All right, so you can have 5 analyses running all at once that you know will finish. So if you have a really large data analysis, UI is a great place to put it. Finally, there's all queue, right? There's no limits on the number of jobs you can run, not 5 in a row, right? It'll give you as many as you can access. I think there are some limits, but they're like 80 or 100. I mean, you could be running 100 things at once, but you can get evicted on this all queue, right? So when you set up the analysis, you have to specify which queue to use, and depending on the analysis that you plan to do, my recommendation is either all queue or UI. All queue would be more of the simulation or the high throughput. UI would be more of the high performance if you're doing a single very large data analysis. Okay? All right. Slots are equivalent to a share of machine resources. So it's like if there's 56 cores on a machine, 1 slot is that 1/56th of that core. If you specify a lot of slots, it'll take longer for it to find a place in the schedule to run your job. So what is a lot? I mean, I have never run into problems, and I've for 4 or 5 or even 8 slots at a time. If you're running a high performance job, a complicated data analysis that runs in parallel, then you may need more. It may take longer to figure out a time it can run going forward. So the other thing about Argon is when you access it, you have this terminal window. You submit a job, and the job will run somewhere. But you have no idea what type of machine it's running on. It's just running on a machine that's going to otherwise sit idle. That machine could be 7 years old. It could be 2 years old. It could be, an Intel chip. It could be an AMD chip. Who knows what it is? And that's why they say it's heterogeneous hardware. So it means you get access to a whole lot of it because it's whatever they've purchased in the past is being maintained. But the downside is that you may not necessarily... You're going to get variation in how long things take. Because sometimes you'll run it on a machine that's slower. Sometimes you'll run it on a machine that's faster. In some rare cases, some applications don't run on older architectures. I haven't run into that issue for the research I've done. If your research is similar, that likely won't be an issue. So I think if you're in the neural network world, that may be more of an issue. Let's move forward now. We can do this. You can do it. Come on, PowerPoint. I hate using PowerPoint, by the way. I've decided it's just killing me. I cannot move forward. There it goes. Okay. You know what? Now's a good time. If you'd like some more information about resources, here you go as a link. Here are some of the places. This stuff is really not useful at the moment. We're going to log in just a moment and show Argon then. But now is a great time to see if you have any questions.
Yeah, I do.
Farhan.
Sorry, it takes me a second always, but to think of the question.
I'm everywhere delayed, so I'm not going to judge you in any way. Let's just put it that.
Okay, so a quick summary of what we've discussed so far. You have certain jobs that what do I call it? Certain ways to access Argon. If you pay for it and if you don't pay for it. And if you pay for it, you can access things called queues, where what you're working on is not going to get kicked out up to a certain point if you're running like a certain number of jobs, right?
Right. Well, let me back up. I'm trying to get to the queue slide, but my slides are broken again. Everything has to run in one queue or another. If you pay for resources, then you end up having your own queue. So like my queue is the Templin queue. And so when I specify jobs to run in Templin, nobody boots me off of Templin. They'll run to completion. There's a similar queue to that for everybody if you don't pay. It's the UI queue. So if you specify the UI queue, your job will run to completion, but you can only run at a maximum 5 jobs at a time.
Okay.
And then all queue will run anything at any time, but you can get kicked off. So if you have a very long analysis that you're doing, all queue will likely end up having that job get evicted because at some point the resources that are where the investor has priority access will need to be used, and that's where you get evicted.
Okay.
So in practice, let me just give you this. For most simulation studies I actually use the all queue itself because most of those, I get access to more of the cores than I have in my own queue. And if they're evicted, it's okay. I just have to restart it. I write my script in a way where it's easy to restart, so I can just run the analysis later. And eventually, after a few restarts, I'll get them all done.
Okay.
If I had, sorry, go ahead.
What if you're just about done with something and then you get evicted?
That's it happens. Right? It happens.
Yeah.
So that 72,000 analysis example I just gave, I ran LQ, and you can have it notify you when jobs get evicted, right? So you'll get emails, 72,000 emails, but still emails. So that then you'll need to rerun the jobs that have been evicted. So I actually created a script to go and see what's been run. So I know things are run if I get an output file. That's how I wrote my analysis. So it checks to see if the output file is there. And then it actually checks to see the jobs that are currently running or scheduled to run. And if a certain version of the analysis is not in either of those, then it will submit a new job for it. So all I have to do is just log in and rerun that script every once in a while, like every day or every couple days, and it will just restart them. And this is sort of a random process, right? What's the probability someone needs the resources? Eventually, you will get to the end of it. Now, I've gotten to the end where I know I may have only a handful of analyses left for whatever reason they're taking a long time. I'll drop those. I'll change the queue from all queue to UI and just run 5 at a time to finish it because those 5 won't get evicted.
Okay. And any time of the year when this is least busy?
It seems when classes are not in session. Although not...
Okay.
Terribly. Well, here's the thing. Like, all of our class now has access to Argon. So in theory, we could be running lots of jobs. So that's going to take up some of the resources. I mentioned that time between Christmas and New Year's. That was a really available set of times. But the first couple weeks of January, right after classes, actually the end of January, right when classes were in session, I found like the first couple days of the week of the first week of class was ridiculous. It took forever to get anything running. So it fluctuates. Although I rarely have seen. I've run a lot of simulation on there, and I've rarely seen all Q not do things very quickly, even during class.
Okay. And last question.
Yes.
Slots. Can you explain those again?
Synonymous with core.
Okay.
So it's basically the computing chip and the memory resources that go with it. So if I'm running so again, let me go back to my Bayes example. Like to run 4 Markov chains at the same time, I ask for 4 slots. And then my programs usually run in R. I use a package called parallel. R will go and send over the information to each of those slots and run those analyses simultaneous. And then when it's done, it brings back the information and goes back. So I just ask for 4.
Okay. Thank you.
Thank you. Anybody else have questions?
So do you mean by the slots is one slot you do one job?
It depends. So your job file itself has to ask for a set of slots. So if you're doing a job that's not a parallel analysis, if you're just doing, let's say you're doing the example we're about to use is IRT, like doing an IRT analysis of a data set. And it's not in parallel, it's just a single, like it would run in serial in R using the MERT package. Then you would ask for 1 slot in your job to run it. If you're like me and you're saying, I want to run 4 Markov chains simultaneous, and I'm actually going to use JAGS, the program JAGS, but I'm going to access it in R because there's a package in R that allows you to run those 4 chains simultaneously. JAGS, R2 JAGS is the package, and there's a function called jags.parallel that makes it work. You'd ask for 4 slots to run that in parallel. Now, if you have another program, HPC mixed may be an example of this in SAS, although I haven't used it. It may say you can specify how many cores you run it on. You'd ask for a slot for every core that you specify in the program itself. But if you're not into that situation where the program is asking you how many cores you need, then you don't need to worry about slots. You just put 1 down. Does that help?
Yes, it helps. Thank you. And also, if let's say we run what we had before, we have 15 permutation and we have 1,000, just as an example. So does that mean we got 15 jobs at the same time if I run?
It actually means we would actually have 15,000 jobs to do it optimally. 1 for each replication.
Oh, okay.
But we would, so the key in this, and this is where I'm going to show you in the example, is to create, well, in my case, R script. It could be any other language that you like. It could even be the shell script language. You create a script that does the work of creating the job file and submitting it for you so that you just run that script and it does all the work for you.
Cool, thank you.
You're welcome. Yeah, it's sort of a little bit of an engineering challenge to get everything in line for it, and it does take some practice. I will tell you that much. But I think it's a valuable skill to learn. Other questions? Okay, now is a great time to take a break. So how about we take a break for 10 minutes? Let's come back with about 5 minutes at the top of the hour. That's 10:55 Central Time, Central Daylight Time. And we will come back then. I say that only to mock us here in this country, for those of us who are outside of it. But come back at 5 minutes to the top of the hour, and we will resume. And if you see my camera off, just know I'm not here, but if it's back on, feel free to ask any questions. All right. Thank you, everybody.
Jonathan, one quick question.
Yes.
Can you also place the lecture PowerPoint out as well? I didn't see it in the icon.
Okay, I will double check that it's there, and if not, I will add it. I apologize for it not being there. Thank you. I'll be right there. Okay, well, let's get back to it. So, well, let's try to get back to it, I should say. Oh, hey, it's moving a little quicker. What do you know? Okay, let's go and access. How do we access Argon is the next thing. I'm going to show you some slides for how to access it with your local computer in just a moment. But the key to accessing it, if you don't want to follow on your local computer, is to use the notebook site. And I'll just show you the notebook site real quick. If you go back to your RStudio server, in the terminal window, if you type SSH, two S's, SSH dash, well, you don't need this on the notebook site, but I'm going to put it anyway just to get in the habit of doing it, dash P40, so port 40. Your Hawk ID, for me it's jtemplin, at argon, hpc.uiowa.edu. We are going to, it says it's going to be adding the host IP address. That's okay. Put in your Hawk ID password or university password. And then it'll ask you Duo again for a push, which will happen. So once again, the key to this, the easy way that everyone should be able to access is by going to the notebook site, going to the terminal, and the command in the terminal is ssh-p40. If you put argon.hpc.uiowa.edu, it'll ask you for your Hawk ID. That's the easy way. But that requires the RStudio notebook site. I'm going to show you some slides that don't do that. And for those of you on Windows, can you guess what's going to come next? Windows doesn't allow you to access SSH by default. But here we go. Let me show you on Windows. Oh, there's the RStudio notebooks. Just mentioned that before. It's like I made these slides. If you don't want to use RStudio notebooks, you have to, on Windows, you have to get a program. Another program. There's an open source program called Putty, P-U-T-T-Y. If you Google or search the internet for Putty, you'll find a link to it. Inside, when you open Putty, you'll see this window that's on the right-hand side that I know, heaven forbid, I actually logged into Windows to have to get this screenshot for you. Dirtying my machine a little bit to be able to do that. But that being said, I should say that I used to love Windows long before I realized connecting to these types of things was so much easier on Mac. Argon, the host name that you need to put in is argon.hpc.uiowa.edu. And again, if you use port 40, you don't technically need to be part of the VPN. If you don't use port 40, it will, once you press open, it will then give you a black box where you have to log in. It says log in as, you put your Hawk ID. The password would be your university password, and then you confirm it with Duo. Once you do that, everything else will be the same that you see here or on Mac or anywhere else, because your terminal window will be on the Linux system. It'll be all Linux commands after that. So that's Windows. You want to know how easy it is on Mac? You hit Command Space, you type terminal. Up will pop terminal. Maybe? I got this spinning beach ball here because my Mac is overheating. And then you type SSH-P40 and your Hawk ID. And actually I set up when you get into SSH and you get into the bash shell, you can put a shortcut in. I just made a shortcut to Argon. but then that's it. You just have it already there, and it's there. So if you have a Mac, go to the terminal window, type SSH-P40, Hawk ID at Argon at HPC, and you're in. Okay? That's the multiple ways of accessing it. Today and for class, I'm just going to keep us on the notebook site, so we'll kill that right there. So today we'll just be here, and whoa, I didn't mean to do that. Ding. Okay. So there you have it. Is everybody able to get access? Following along? Thank you. I would also say thank you for attempting to access this last week. For whatever reason, there were a handful of you that the HPC group didn't authorize. And so with a couple emails, we got that fixed. So hopefully today will be a little bit smoother. But now that we're in on this terminal, you'll see what's shown here is another $sign. So it looks very much like your terminal in R. In fact, if I create a new terminal, what is the difference between this terminal 2 on my machine, and this terminal? How do you tell the difference? It's in the bracket. It gives me my Hawk ID at Argon, and it's Argon login 2. This is what's called a login node, which it's where we log into the system itself. So you'll know you're in Argon if you see that bracket and it says Argon on it right here. The alternative is if I switch over to my other terminal, you'll see I'm jtemplin at jhub-psq at blah, 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 not Argon, right? So you know you're in Argon if you see Argon in the brackets right there. So in Argon, it is just like all the other Linux systems that you've seen before, including the other terminal in the HPC. So all the commands we've learned before, like ls, if I type ls-la, I see all the contents of my home directory. If I type pwd, I see my home directory, and so forth. And in fact, one of the things you'll note is in my home directory, right here is the Argon demo file that we copied over using SPC. So if you type ls in your home directory, you should see an argondemo.tar.gz if you successfully completed that step from before. And if you don't see that file there, when we're done with class, send me an email and I will help you get it there. Okay, we'll be using that next week. Any questions on logging in so far?
Oh, I think I got it now. I have to reestablish it. Okay. Oh, my question was maybe do I have to redo it? But it says yes. So.
Yeah, the logging in, if you're it will often time out and just kick you off. So you have to often do it, which is sort of a pain, particularly because you have to use the two-factor authentication. But it eventually will get you there. Any other questions? Okay. Let's keep moving along with our slides here. I'm logged in. Now what? Again, Argon is a batch queued system. In fact, if you'd like to look at, and this is dangerous, but I'm going to try it. I'm going to move this over to the side. If you would like to see the current jobs that are scheduled in Argon, type the command qstat, hit return. It'll take a moment. It may take many moments. And it will spit out a whole bunch of commands. There it goes. Look at that. That right there. Those are all the jobs that are currently listed in Argon right now. That's everybody's job that's running. You can see who their user is. But what you end up seeing here, this QW means it's waiting. This is the number of slots they requested. So many jobs have 56 slots itself, which is like the whole machine for a more recent version of the machine. So you just see a whole bunch of jobs that are listed. At the top of this list, if it were running, you'd see an R here, and it would tell you when it started running or how long it's been running for. So that is the set of, this is the queue. This is literally where a bunch of the jobs are set up. And actually, I believe this is the queue. Those are supposed to be, Actually, I'm not sure what those are. Anyway, it's been a while. So, jobs, it's a queued system. The next question is, how do you actually go and submit your job? Well, we'll show that in just a moment. There's a thing called a job script. If you want to remember just a couple quick things about Linux, again, just to remind you, pwd shows you the path of the current directory. When you log in, it puts you into your home directory itself. If you want to change the directory you're in, cd, and then you put the name of the directory to change it. If you see a tilde/, that's an absolute path. The tilde refers to where your home directory happens to be. So we often use tilde/s in our files that we share with each other, because if my home directory is, go to it real quick, pwd is user/j template. Yours will be different. If I tell you to access the Argon demo file, it will. If I use tilde/Argon demo, whoops. If I use that link right there, tilde/, that will work on all of ours so long as you put the Argon demo in your home directory. Right? So that's the nice thing about the relative path. There we go. And alternative to relative path, you can use the user/whatever for your own. Moving forward, there are file operations. CD is change directory. LS is list, so you list the contents. MV is move. CP is copy. RM is remove. And I believe there's a previous lecture you can go and refresh yourself with for those commands. If you work in Argon, you will be very, very familiar with these, because you'll need to move files around using the command line. One other thing I should note, it's not possible in our class. However, if you sign up for an RStudio Notebook site, where you log in not with, here, let me do this. Whoops. That's not what I wanted. Let me go to another site here. This is an actual nice feature of the Notebook site. If you sign up for your Notebooks account outside of class and you log in under the interactive research link, what it will give you once you log in, somebody should have a betting pool as to how many times I have to use Duo two-factor when I'm teaching this class. I think I'm using it probably 50 times a class period. There is an option under this server here to mount the HPC home. And if you click yes to that, and you pick the R, I'm going to pick the R image right there. What ends up happening is your Argon system will show up in RStudio in the files window. So you'll be able to see Argon's files while you're using RStudio. That is a really cool advantage to doing that. And if you haven't signed up for a Notebooks account yet, do so. Go sign up for one, because if you're using Argon, it goes a lot better when you can see your files outside of the command prompt. So again, I'm showing you this. Maybe. There it goes. Must learn to have patience. Patience. Yes, close this file. Anyway. Close. Here, it puts a folder in that's HPC home, and that's Argon right there. There's my Argon file. There's my Argon demo that I uploaded right there. So, once again, if you'd like to see Argon's files in the RStudio window on Notebooks, you have to have a regular Notebooks account and sign in under Interactive Research. Okay, moving forward. Job scripts themselves, I'm going to go into more detail on those next week. Let me give you an example of one for now, though, just to show you what it looks like. And I'm going back here. not going to know that. All right, let me type. Here it is, nano test.job. Nano is a text editor. This is a job script. There's a bunch of commands that show up with a pound or hashtag and $sign. It tells it's a command. And each of these we're going to be covering in more depth next week. But at the bottom of it, there are other commands. It culminates with us running an R script. And we run an R script using there's two methods of running R scripts in R. One is R script and one is RCMD batch. Each of them have a different use scenario. I use R script for most of what I do. So job files are what happens. You create a job file. This is an example. If you'd like to see an example, actually, let's follow along with this example. In your command window, type the following: cp, let's do this, cp /rs /HPC training. And I believe it's /sleeper.sh and a period. So what that will do is copy a shell script. If we type nano sleeper.sh, we should see a shell script. Yep, there it is. And this gives you all the options, and all it does is it just waits and does nothing for 60 seconds. So this is an example file that teaches you how to run things if you want it to do that. You'll note, and actually, here's a key. There's an email address up here that you would submit a file to. You really want to change that, otherwise Sai Kumar Ramadugu will receive emails every time we run this, which is not good. I'm going to put my J template there. So once again, if you're following along and you're trying to do that, yes, you can copy the sleeper script using this command: cp /rs /HPC training /sleeper.sh with a period, and then a space and a period. That copies the file from that folder to the current folder that you're in. If you want to look at the file, I like to use this text editor named Nano. So you type Nano in the name of the file, and it lets you look in it. If you're doing this, if you're wanting to follow along, go to the line that says email address to send to and put your Hawk ID in front of you, Iowa. Be sure to do that. Otherwise, the person whose email there will get very, very angry with me. I believe using this next command down here, it says select the queue to run in. I'm going to change it from IHPC to all.queue. To get out of Nano, you type the command Control-X. It's not working. And then you hit return to save the file. That is the job. So now, if you'd like to submit the job to the queue, you type the command queue sub, and then you type sleeper.sh. And you hit return, and what happens is that job is now submitted. If I type qstat-u and my Hawk ID, you will see eventually its state is T. I don't know what that T state means. Terminated, maybe? Not sure, but you'll see at least it existed at some point. So that was it. So that's how you submit a job and how you build a job file. Again, next week we'll go through the nuances of how to build them more specifically for what we do. In fact, in the script that I have, I use R to write the job file for us. So we're actually going to build that job file in R as we go forward. Questions on that?
I just have one quick question. Sorry.
Yeah.
So when you were doing the resource selection directives, when you wrote, I know it was like dash Q. You wrote something else. My computer froze at that very moment. I don't know what you exactly typed when you were in Nano. I didn't know if I should.
Yeah. Let me go back to Nano real quick.
Thank you.
Under the dash Q, you want it to say all.q afterwards. That's to run this job in the all Q queue.
Okay, thank you. Sorry about that.
No, thank you for asking for clarification. I appreciate it. Other note, though, and this is key, got to make sure that email address is yours. What this job should do, if you've made that email address yours, is it will send you an email at the beginning, at the end, and then if it was suspended, of the job itself. Next week, we will also talk about how to put a filter in your email so that you can filter Argon files to a folder. That's what I do. I have a specific folder on my email system where I use Outlook to take the message and just drop it in the folder when it's received, and then it doesn't clog my inbox up. Other questions? No questions. Moving forward. We're almost done today, and then we'll have Harry give a talk, give her paper. Maybe? So once you submit it, you can type qstat-u and your username or your Hawk ID, and it will show you your Hawk ID. You can also check for output files. So if I type ls, you'll see in my folder there's a sleeper file here with an O and a bunch of numbers, and a sleeper file there with an E and a bunch of numbers. Those are the two types of output files. Tree is for transferring. Thank you, Shihong. Those are the types of files that get created. O is just output. So if I type nano and sleeper.o and then fill that number, by the way, with the job number, you see right up here, my job ID number is listed as the same at the end. This tells me these are the output. I had it right. There were echo commands at the bottom of that sleeper file itself. One that said when it started, one that said when it ran. And then the E file is the error file. So if any errors were to appear, you would see them in this E file. I don't see any errors, so I'm happy about that, and I move along. And actually, I'm surprised, given my track record in this class, that there are no errors. Questions? Okay, so you submit the job with QSub. Before the job is run, you might hit QStat to see what's going on, what happens with it. That's to show you the status of all the jobs that you have. And then once the job is running or has finished, you will find two files in your directory, which is an output file and an error file. The output file will have any text that comes out of the program itself. The error file will have any errors that may have shown up in the process of doing that. And then we're done.
Jonathan, there's a question in the chat box.
Oh, yeah. How do you exit Nano? Exiting Nano, hit Control X. Now make sure, Lexi, you use a Mac, so make sure it's the control, not the command. And then once you exit, if you've made any changes, hit Control X, it'll say Save, Modified Buffer. If you click Yes, you will overwrite the file with hit Return after that to write it to it. So Control X starts the shutdown in Nano. Well,
I forgot I was pressing command.
Thanks for alerting me. Farhan, thanks for letting me know about the chat window. And Lexi, thanks for asking. Welcome to the world of text editing on the command line. There are other text editing methods. And this is sort of, how do I want to say? You can tell how much a person spends time on the command line by which text editor they use. Vim or Emacs are sort of like the pro level stuff. I'm not a pro. I use Nano. you can get into a bunch of stuff with it. A lot of rabbit holes to go down. If you really want to go down rabbit holes, try the command tmux. It will allow you to run multiple command lines and keep them running when you log out and everything too, but let's just not do that. Okay. If you wanted to stop a job, if you ran something and you realized something went horribly wrong, you use the qdel command, and you type the job number afterwards. We don't need to rerun this to do it, but actually I'll do that real quick. Let's imagine I do qsub sleeper.sh, and I see that once it submits, I will get a job number. There it is. Okay, so we type, if we wanted to delete it, we type qdel 4370433. We type the job ID number to delete it. How do you find the job ID number when you're submitting a lot? It's the qstat command would have done that as well. All right, so this qstat command right here shows you your job IDs, and you can delete it that way. There is another way of using qdel. If you started a whole bunch of simulations and you realize you had an error in your code, to delete all of them, you can type qdel-u and your username, but that will delete every single job you have. That's the nuclear option that will blow it all up. Okay? And remember, nuking things is not okay, usually. Other questions you may have? No questions. All right, finally, if you try to run R, it will not tell you anything. Cannot find it. Turns out to figure out the software to run an Argon, what you have to do is load what's called a module. Modules are how Argon administers each of the programs to run. And so for us, if you type module avail, what you will see is a whole bunch of programs. And hey, look, there's some R right there. Where it says more, if you hit the space button, you'll be spacing for a while. To get out of this, type Q. The letter Q will exit all of it. For us, what we need to do to run R, for instance, would be module load R. Takes a moment. Now this, by the way, will, but here, once it does that, if you type R, you will be in R. You'll note it's version 3.5.1, so you may want a more advanced version. We'll get to that a little bit later. Actually, we'll get to that next week. There's R. Now, let's say you wanted to run SAS because you have a big job to run in SAS or Stata. You can type the word module and then the word spider and type some of the letters of the word that you want. Here's SAS. It tells you you can use SAS /9.4. So you want to run SAS? Type module load SAS /9.4 underscore TS1M2. The same thing that you see up here. I typed all that, but it's not actually typing. There it goes. So when you see there, now it's loaded. If you type SAS, guess what? You're in SAS now. Oh my goodness. Now I really need to know how to get out of SAS. Okay, how about there? Yeah, Control C. T for terminate. Yes, I'm sure. There we go. I use SAS. If you use Stata, you can do module spider Stata. And nope, can't find Stata. I thought it was on here, but it may not be available. Anyway, long story short, there's a ton of software on the system itself. You can run things like MATLAB or whatever else. You can find modules with module avail. You can load them. You can also unload them. And depending on the type of software you're using, You may have to load or unload things. I will say for us, for our purposes, I use JAGs a lot or Stan a lot. You'll have to load those modules before you load R. But I'll get to that later. Or you can send me a note. I'll leave those alone. Now, one common issue you might encounter if you're using Windows is you might be getting weird errors and don't see anything wrong with my file. Well, if you edit text files in Windows, come to find out, Windows puts a weird character at the end that Linux systems don't like. And so if you're on, so if you didn't do what we just did in this Linux example, where we just stayed in Linux for everything, but if you downloaded Sleeper to your Windows system, edited it, and then re-uploaded it, you might see a bunch of crazy characters at the end. Turns out those are characters that Windows problems gives you. So you can either use a text editor on Windows that allows you to save and have a Unix line ending. Notepad++ is one that does that. You can edit your text files directly in Argon. That's what we just did. Or there's actually a command in Argon called DOS to Unix that will convert the files and take those trailing characters off. But if you're seeing weird errors, that may be it if you're a Windows user. Yet again, another reason why I really switched from Windows back in the day. Okay, if you need additional help, if it's a cluster issue, you can email them. They'll help you pretty quickly. If it's something with respect to class, email me. There's a whole bunch of documentation online, and their wiki is pretty good for that. But next week, we're going to follow that demo, and that's where we'll be. So with that, does anybody have any other questions? Wonderful. So now